Welcome to my class. I'm Drew Collop. In today's class, we're going to examine graphing of data. When working in the laboratory, data is the key thing you'll be collecting. It is important you understand how to properly graph that. When we're collecting data through observation or experimentation, this data is referred to as empirical data. This raw data is not how most people view your data. What you will want to do is plot a graph demonstrating the relationship between the independent and the dependent variable. Let's review the steps for plotting empirical data on a graph, also known as plotting your raw data, to see if there's a relationship between your independent and your dependent variable. So your independent variable, this is your x value. Your dependent variable, this is your y value. Again, your independent variable, this is a value you select. The dependent variable, this is the value you measure after you apply the selected x value. When we determine a y value for an expected x value, this is a set of ordered pairs. If it's x and y, you can represent it as a coordinate, x, comma, y. We determine the appropriate scale for our axes and we label it. We label it with the appropriate variable, and if there's units, label that on the axes as well. Plot your set of ordered pairs on the graph. Connect it with a line of best fit, and then create a title so it's easy to understand. Do not use the word versus in a title. If your graph is temperature and time and you say this is a graph of temperature versus time, that is the worst title you could possibly imagine. It doesn't bring anything extra to the table. Why? Because I can just look at the axes and your labels and I can see what that is. So instead, be quite descriptive of the title. Scientific articles are the primary way science is related between scientists and the general public in this day and age. I don't know if you've ever read a scientific journal. If it is not what you're absolutely interested in, it can be very dry and very boring. Having a graph that shows a relationship with an appropriate title can be a wonderful thing. That way, all information can be determined about what you did and the results of your experiments by just looking at your graph. Let's look at an example here. This data is all made up. It's not real. It's an example. So let's say we turned on an oven and we measured the temperature over time. Maybe it's a very hot oven, perhaps a smelter, I don't know. Something that goes to very high temperatures. We have the time and we have the temperature. Time will be your independent variable. I'm selecting the time. I'm going to record data at 0 hours when we start the experiment and every 1 hour after that. I've chosen that. I could have chosen other times. I could have chosen to collect data every 30 minutes or every 2 hours or every minute. So this independent variable, this is what you select. When I make a measurement, I'm measuring temperature. This is my dependent variable. So this is dependent. This is what I'm measuring. The temperature of the oven will depend on the time I record the data. Prior to this, we've been working with an x and a y coordinate. We don't have x and y here. We have time, which is lowercase t, and we have temperature, uppercase T. Please note, I selected these on purpose to indicate that time is usually represented as a lowercase t, and temperature is usually represented by an uppercase T. Be aware of that. Also notice the units are in there. H stands for hours. It could have been any times, seconds, minutes, years, could be anything. Also temperature, it's in degrees Fahrenheit. It could have been in degrees Celsius or in Kelvin. Where are our set of ordered pairs? Well, here they are. We have 0, 102. 0, 102. We have another set of ordered pairs. We have 1, 463. And moving down the line, you can see these two values are related. My time and my temperature. Let's plot this now on a graph. Normally when you're dealing with data, your origin is in the bottom corner here. I'm going to draw my horizontal axis along here and my vertical axis right here. Let's label it now. What do we have? On the horizontal axis, this is your independent variable. This is in time. T is my variable, and my units are in hours. For my vertical axis, this is my dependent variable. What I choose for my time will depend on what my temperature is. This is temperature, uppercase T, and my units are in degrees Fahrenheit. Let's put my scale on here now. Remember, we want to try and maximize the use of this. There's nothing worse than seeing a graph and it looks like that. That's all the graph someone has used. Or other graphs look like that. You have a data point way over here. So try and plan out your scale before you plot your graph on there. That way there's no data that falls off the graph and you're not creating a little graph that's this big. That shows you nothing. The best way to do that is look at your range and divide by the number of squares you have to work with. So let's examine time first. So time, we're going from 0 to 10. So my range is 10. So in this case, my range is 10. How many boxes do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I have 15 boxes. I divide that by my 15 boxes. When I do that, I get 0.66666 over boxes. What this represents is that every box is 0.666 units. I don't want to place 0.666 on my graph, but if I multiplied that by 3, this works out to 2 units. So we can say every 3 boxes is equal to 2 units. This is 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Look at that. Perfect. I'm going to utilize the entire x-axis. Just to clean it up a bit. Now let's put our scale on our vertical axis. Here we're going from, we'll say we're going from 0 all the way up to, we'll round it off to the nearest whole number, 1900. So our range here is 1900 degrees Fahrenheit. We're dividing by how many boxes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 boxes as well. We work that out. We get approximately 125. We'll round up to the nearest big number here. We'll go up to 150. So we'll say every square is worth 150. So here I will jump to, see, 2 squares. Each square is worth 150, so 2 squares is worth 300. 600, 900, 12, 15, 18, and we have, running out of space here, 2,100. Now that we've put our scale on there, we've labeled our axes, let's put our data on there. First data point now, 0, 102. So on my horizontal axis, I don't move anywhere. This is time 0. This is when the experiment begins. So it appears the oven was already at 102 degrees when we started the experiment. 102, notice we have to do our best guess. Here, this would be 150. So 102 is going to be somewhere about 2/3 of the way up, right there. We go to the next point, 1. This is 0, this is 2. So 1 is right there in between. We go up to 463. That's 300. That's going to be 450. So it's just slightly above that. We then have 2, 748, 6, 750, right about there, just below 750. Next up, we have 3 and 1010. Again, the 3 is going to be right in between the 2. Moving up here, it's 900. That would be 1050, so right about there. Moving along, we go to 4 hours, going up to 1210, so just slightly higher than. And then we go from 5, right there, all the way up to 1370. 12, 1350, so just slightly above the 1350. 6, 1510. Right about there. We have 7 and 1590 in between the two. 1590, this would be 1650, so we're plateauing off here. Notice that. We then have 8 and 1710. This would be 1516, this would be right above. And then 9, 1770, 9 is right here, 1770 right below that one there. And then lastly 10 and 1830. Here we have our data points here. If you like, they're kind of small. We can draw little circles around them to try and better show where they're at. And now let's connect it with a nice smooth curve. So now we've plotted the line of best fit. You can see it's a nice smooth curve. It initially ramps up, and then as it gets hotter and hotter, it starts to plateau off. Let's put a title on this. What's a great title? Temp versus time, right? Wrong. Don't ever use a title with the word versus in it. Let's write an appropriate title. Temperature change in a Samsung ES1000 oven over a 10-hour period. Sorry for cramming that in there. Notice this title is very descriptive. It tells us what's going on. It tells us what's increasing, right? If I just look at temperature and time, what am I measuring? Am I measuring increase in the human body? Am I measuring the temperature of the sun? Very important you clarify that in the title. I'm measuring the change in an oven. And notice I'm specific here. I don't know if this is a real oven. I'm just making this number up. I have potentially the model number, an ES1000. Very important in science that others can repeat your experiments and get exactly the same results. That's the only way science works. If you're the only one that can do that experiment and get those results, no one will believe you. That's why writing your protocols down and being specific about what you're doing is so very important in working in science. Here's some data looking at conductivity of different concentrations of acetic acid at 25 degrees. We have our independent variables. In this case, we've made up these solutions. And then we have our measured values. These are our dependent variables. So we make up these solutions, we measure the conductivity in there. Independent, I choose. Dependent, the measured values. You could create this as a set of ordered pairs. These two would be a pair. These two, these two, these two, and these two. You could treat this as X and Y, but we don't have X and Y here. We have concentration and we have conductivity. Try this on your own right now. Try and make the appropriate scale, finding the range, dividing by how many boxes you have to try and maximize the use of the graph. Label the axes with the appropriate units, plot the data points, connect them with a nice smooth curve, and then put an appropriate title on the top. Try this now. Let's take it up. Let's determine the range. Our range here, we're going from, we'll say go from 0 to 0.1. And our range here, we'll say we're going from 0 to 210. So 0.1, there's 15 boxes divided by 15 boxes. Over here, 210 is my range divided by my 15 boxes. Top value is my range, and the bottom value is how many boxes there are in my graph. Range, number of boxes. We work this out, we get 0.006 repeating. Let's multiply that by 3, and every 3 boxes will be worth 0.02. So 3 boxes, 0.02 units. Over here, we divide that out, we get 14, which is pretty close to 15. So every box is worth 15 units. Let's graph that now. Our scale here, which one goes where? Do I put concentration on the horizontal axis, or do I put conductivity on the horizontal axis? Remember, I always put my independent variable. I've chosen the concentrations. Therefore, that is independent of the experiment. I've selected it. Therefore, that is your horizontal axis. We said that every 3 boxes will be worth 0.02. So 0, next up 0.02, next up 0.04, 0.06, 0.08, and 0.10. This is my concentration of acetic acid, and it is in percent weight by weight. If you don't quite understand what percent weight by weight is, don't worry. We'll cover that later on in this course, and you'll do it in your biology and your chemistry classes as well. For my vertical axis, I said every box would be worth 15. So let's put that on here. 30, 60, 90, 120, 150, 180, 210. Let's label this axis now. This is the conductivity. And it is going to be in millisiemens per centimeter. That is the units for conductivity. I believe you'll do some of that in your chemistry class. Let's put our data now on this. Let's start at the bottom. Let's start with this one here. 0.1 and 209. So 0.1 is right here, and 209 just beneath that. So right up there. We have 0.3 and 114. 0.3 is somewhere between those two, and 114, we're going to go up to 120. That's going to be right about there. Next up, we have 0.1 and 63. 0.1 is in between there. 0.1 and 63, just above that one. We then have 0.003 and 30.6. So 0.003. Remember, when we calculated the scale, about halfway. So we're talking about right about there. It's getting quite challenging now, which is why I started with the big numbers. Now we have our last unit, 0.0001 and 15.5. So it's not quite 0, but almost. And we're talking just above that value right there. Let's draw some circles around that and connect it with a nice smooth curve. You can see a similar effect here where as it increases, it's going up, but it begins to plateau off. Let's give it a title. Conductivity versus concentration? No. Conductivity of acetic acid. Acetic acid, I've run out of space here, at 25 degrees Celsius. You shouldn't have it written like that. Hopefully you can plan yours out a bit better. So some key features here. Notice it has an appropriate title. The word versus is not in there. It gives us more information than just what's in the axes. If I titled it conductivity versus concentration, it doesn't tell me anything extra. I can look at the axes. We have that property labeled. I can see the concentration is in percent weight by weight, and I can see the conductivity units are millisiemens per centimeter. In addition, notice my axes are to scale, and I've tried to maximize the use of that scale. I put my data points on there. I connected them with a nice smooth curve. So please notice, you can look at the table. The table doesn't say much. You look at the numbers, it's just a bunch of numbers. But you put that into an appropriately designed graph, you can look at that and you can see some relationships between the concentration and the conductivity immediately. So make sure you use the appropriate graph to demonstrate your data. If you have the best data and you can't present it properly, it's going to have no impact at all. Let's talk about spectrophotometry. This is something you're going to use quite a bit in our biology and our chemistry labs. A spectrophotometer, this one specifically called a Spec20, it measures the intensity of a light beam. So what we can actually do is we can put a sample of a chemical into a test tube, place it in the machine. Here's our solution with our chemical inside. We have a prism that splits up the light into different wavelengths. We can then shoot different wavelengths of light. Wavelengths are also known as colors of light. But color is just a construct that your eye makes to determine different wavelengths of light. When it hits the solution, a certain amount of the light will be absorbed by the molecules inside the solution. The light coming in will be of higher concentration than the light coming out. We then have a detector, and we can determine what our percent transmittance is, how much light gets through the sample. This is a wonderful technique because we can determine many different things using a spectrophotometer. Number one, if you don't know what the solution is, we can measure the absorbance of various wavelengths of light, and depending on which ones absorb more or less, we can determine what that chemical is. In addition, once we know what our Amax is, our maximal wavelength of absorbance, we can actually determine the concentration of the solution based on how much light is absorbed. This is a key skill to have, and you will learn this in both biology and in chemistry. I've talked about this before. This is called a Spec-20. This is an old school spectrophotometer. We use these in the lab for a very long time. They're analog. You really had to understand how this worked. That's why we kept using it, because it was a great learning tool for our students. However, they're very old and they don't manufacture them anymore, and they're starting to break down. So we've now upgraded to digital spectrophotometers. You'll be using those in our labs moving forward. I bring this up because I want to show you something. There's a relationship between the amount of light absorbed and the amount of light transmitted. If 100% of light is transmitted, then no light is absorbed. If all of the light is absorbed, then there's no light that's transmitted. So there's a relationship. It's indirect. However, the scales are very different. This is what it looked like on the spectrophotometer. We had percent transmittance on the top, and we had absorbance along the bottom. Notice the scales. For percent transmittance, this is a linear scale. Every box here is worth 1. On the bottom, however, it is not a linear scale. This is a logarithmic scale. There's actually a mathematical relationship between these two. The mathematical equation here is A equals 2 minus the log of percent transmittance. So if I want to know my absorbance, I just sub in my percent transmittance, I log it, I make it a negative value, I subtract it from 2. Transmittance is easy to read. This is much easier to read across the board. When you get down to low percent transmittance, your absorbance is very hard to read to get an accurate number because it's a logarithmic scale. What we did in the past is we would record the percent transmittance, sub it into this equation, and then get your absorbance. I guess I haven't told you yet why you'd want to do this. There's another equation, A equals ELC. If we plug in the absorbance, we know the light travels 1 centimeter in the device itself. This is called an extinction coefficient. There's a specific number for every chemical. There's a book called the Merck Index. It gives you them all. Don't worry about that for now. But in the end, what's important is right here. This is my concentration. So if I know the absorbance of my chemical, then I can calculate the concentration of that chemical. That is why we would record in percent transmittance and convert to absorbance. However, with the new spectrophotometers, it's all digital. It'll give you the readouts, either percent transmittance or absorbance. To ensure you understand this, most of our labs with using the digital spectrophotometers, we will still require you to record your data as percent transmittance and then use the formula A equals 2 minus log percent T to calculate the absorbance. Let's look at an example here now for a chemical. The chemical in question here is cobalt chloride, CoCl2. Notice the O is lowercase, therefore that is not carbon oxygen, that is cobalt, CO. We use the spectrophotometer. We determine the percent transmittance at different wavelengths. We then use the formula A equals 2 minus log percent T to determine the absorbance. Again, this formula is here. We can use this formula if we know the absorbance. We can calculate the concentration. Here's our data. So this data is collected for various wavelengths. Wavelengths along here. So we have a wavelength of 400 all the way up to 640. If you wanted to convert this to a color, something like that, that's not perfect, but it gives you an idea of what the colors might look like. You won't actually see the colors. The beam of light is very small. So from the machine, we measured percent transmittance, and from the formula, we calculated the absorbance. Let's now make a graph of that right now. Notice I have 3 sets of values. So maybe your first question is how do we put 3 sets of values on one graph? Let's do that now. First, let's put our horizontal axis on. And here we're going to have wavelength. This is my independent variable. I've selected the wavelengths I'm going to use. For wavelength, my range, I take my maximum minus my minimum, and this is going to be 240 is what I get as my range. There are 15 boxes, divide that by 15, and I get here 16. We're going to round it up. We'll say every box is about 20. Notice this graph will not start at 0, 0, the origin. I'm going to start right here, 400. Every box is worth 20, so every 2 boxes is worth 40. And that should get all of our data on that graph. Our label is wavelength. Lambda represents wavelength, and our units are in nanometers. Let's plot percent transmittance first. We'll do that as our vertical axis. What do we have for range? Well, it goes from, it's a percentage, so we'll go from 0 to 100%. And there are 15 boxes, so each box is 6.66666. We can multiply that by 3, and we get 20. So every 3 boxes is worth 20. We're going to start this one at 0, though. 1, 2, 3, 20. 1, 2, 3, 40. 1, 2, 3, 60. 1, 2, 3, 80. 1, 2, 3, 100. Making sure we maximize the use of our graph. Let's label that axis. This is transmittance, and it is in percentage. Let's now plot that data. So we're going to use these two, so on and so forth. We have 498, way up there, close to 100. We have 420 and 85, right about there. 440 and 71. 460 and 54. 480 and 47. 500 and 40. 520 and 39. So it was dropping down. Looks like it's plateauing off now. 540 and 52. It's going up now. 560 and 70. 580 and 84. 600, 88. 620 and 91. And finally, 640 and 97. Put some circles around that. And we connect it with a nice smooth curve, something like that. So this is my percent transmittance. How are we going to put on there our absorbance as well? What I can do is I can build another vertical axis over here. And this here will be my absorbance. Please note, there are no units on absorbance. It's one of the few values that don't have units with it. Let's look at our range now. We're going from 0 up to a maximum of 0.4. So our range is 0.4. There are 15 boxes. This gives me 0.02666 repeating. We will round that up. So every square will be worth about 0.03. If I multiply that by 3, I get 0.1. So every 3 boxes will be worth 0.1. 0, 1, 2, 3, 0.1, 1, 2, 3, 0.2, 1, 2, 3, 0.3, 1, 2, 3, 0.4, 1, 2, 3, 0.5. Now we're going to use that set of ordered pairs. Again, we're working with exactly the same independent variable, but now we have a different dependent variable. So let's plot that now. We'll do that in green. We have 400 and we have 0.01, very low, almost 0. We have 420 and 0.7, so it's going up. 440 and 0.15, so now it's going up quite a bit more. 460 and 0.26. 480 and 0.33. 500 and 0.4. 520 and 0.41. 540 and 0.28. 560 and 0.16. 580 and 0.8. 600 and 0.05. 620 and 0.04. And lastly, almost back down. Let's put some circles around those data points. Sometimes it can be hard to see what's what when the lines cross. Nice smooth curve, something like that. When you have multiple data on one graph, it's oftentimes important to write what's called a legend. So I will say we have percent transmittance and we have absorbance. What we'll write is percent transmittance is in blue. There's your data point and there's your line. And absorbance is in green. There's your data point and there's your line. Otherwise, it can be quite confusing to the reader for what is what. What would be a great title for this? Well, I already have a great title. Right here, absorption spectrum for the stock solution of cobalt chloride between those wavelengths. And I maybe would write that as figure 1. Please don't call it a graph, it's a figure. And I would just write that up above right here. Notice it's not wavelength versus transmittance versus absorbance. That doesn't give me any additional information. It tells me it's an absorption spectrum. That's what's in green. It tells us the absorbance. When working with a new chemical, oftentimes you have to make an absorption spectrum. It tells us the concentration of the solution. It tells us what the solution is. It tells us the range of the wavelengths. You're going to do this quite a bit in the laboratory, getting an absorption spectrum. What you want to get from your absorption spectrum is what's known as your A max. I think I said it was 0.4 before. It's not. This number is actually higher. It's your value of maximal absorbance. You can see it on your graph. It's right there. When using this chemical in the lab, you will want to use your A max wavelength. So for this particular chemical of cobalt chloride, you would set your spectrophotometer to 520 nanometers in terms of wavelength. This would give you your biggest dynamic range. If I chose a very low wavelength, like 640, it's not going to change much. Therefore, I want to pick the biggest absorbing wavelength so that I can see the biggest change between my measurements. Here we took two different sets of dependent variables and we plotted it for the same independent variable. We made sure we put the proper scale on the axes. We put the units in where applicable. Remember, absorbance is one of the few things without units. And then we put our data points on and connected a nice smooth curve. And from this, you can see the relationship between percent transmittance and absorbance. It is an indirect relationship. As transmittance goes down, absorbance goes up. As transmittance goes up, absorbance goes down. You can see this from the graph. Compare the blue and the green lines. The last topic of today is going to be graphing of formula. If we're given a formula, for instance, P equals I squared R. This is power is equal to the current squared multiplied by the resistance. What we do, we substitute in our units for the independent variable, and we determine the dependent variable. We then plot the ordered pairs, connect it with a nice smooth curve, label your axes with appropriate units and a suitable title. Here's example 4 here. So graph the power and the current using a resistance of 10,000 ohms. So this is already set for you. So what you should do is sub this in. This gives me the power is equal to 10,000 multiplied by my current squared. As you can see, as I change the resistance, this formula will change. What I'd like you to do now is I'd like you to plug in your independent variable, this current. I'm selecting the current. I'm calculating the watts. We're not doing this through experimentation. We're doing this through a formula. Complete this table, including units, and then make an appropriate graph. Give that a try now. Let's take it up. Current, it is I, and my units is in amps. Power is P, and this is measured in watts. Now, if we fill this out, we plug these values in here. We plug in 0 for I. 0 times 10,000 doesn't matter. This is going to be 0. Plug in 1 for I. 1 squared is just 1. This gives me 10,000. Moving forward, 40,000, 90,000, 160,000, so on and so forth across the board. I'm not going to fill these all out because there's an easier way to do this. Maybe you didn't do that. What I'm going to do is I'm going to put a multiplier in. I'm going to say this is times 10 to the 4. 0 times 10 to the 4 is 0. Let's convert this over to what it would be times 10 to the 4. This is just 1. 1 times 10 to the 4 is 10,000. This would be 4, 9, 16, 25, 36, 49, 64, 81, 100. When you made your graph, it can be quite difficult to put your vertical scale on there with such large numbers. By using a multiplier, it can clean up your graph quite a bit. Let's graph that now. We have our horizontal axis. We have our vertical axis. What goes where? Current is my independent variable, so it goes along the horizontal axis. Current, and it is in terms of I, and it is in terms of amps. Therefore, my power is my dependent variable as P, and the units is in watts. And I'm going to put a multiplier in, times 10 to the 4. This tells me whatever number I have on my scale is, I have to multiply that number by 10 to the 4 to get the actual number. In terms of range here, I have 10 divided by 15 squares. This gives me 0.666 repeating. Multiply that by 3, gives me 2. So every 3 squares is worth 2 units. 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I'm maximizing the use of that axis. Here now, we're going from 100. Say 100 divided by 15. This gives me 6.66666. We multiply that by 3, gives us 20. So this tells us every 3 boxes is worth 200,000 units, or just 20 when we say 10 to the 4. Go up 3, 3, 3, 3, and 3. Maximizing the use of the space here. Now let's plot this data on this graph. 0, 0. So we have an origin here. Guess I should draw 0 on that side as well. It goes through the origin. 0, 0. No current, you get no power. That makes logical sense, right? We then have 1, And we have 1. Almost 0, but not quite. We have 2 and we have 4, right about there. We have 3 and we have 9, slightly less than halfway. We have 4 and we have 16, right about there. 5 and 25. 6 and 36. 7 and 49. 8 and 64. 9 and 81. And lastly, 10 and 100. Put your circles around there to try and indicate where those data points are. Then connect it with a nice smooth curve. Let's give it an appropriate title. Power produced by current through a 10,000 ohm resistor. So it gives us additional information. If I just wrote power versus current, it doesn't bring into play the fact that we're using a specific resistor. And by changing that resistor, it changes the graph completely. You can also quickly see a relationship. As we increase the current, initially it slowly rises, and then as our amps go up, our power increases significantly. There's a relationship between the amount of current you run through this resistor and the amount of power you get out. Remember, very important to make sure you label your axes with the units. Try and maximize your usage of the axes. And don't use verses in your title. Make sure you use an appropriate title. Today, we built on those graphing basics and we started to graph empirical data, that raw data. This is something you're going to be doing all the time in our laboratories. You'll be going in the lab, you'll be selecting your independent variable, you'll be doing a measurement, collecting your dependent variable, and then you will graph that relationship to see if there is one. Is the relationship between your independent and your dependent variable? Graph it and you can see right away what it looks like. By looking at raw data, it's not as obvious what the relationship might be, but by graphing it, anybody can see what's going on. We will be doing a lot more graphing throughout this course, in your other courses, as well as future semesters, and if you go into science as your chosen career, you'll be doing this all the time. That's all for today. Until next time.